So at last now, we're ready to start to talk about these trigonometric integrals, which is the new topic here in section 3 in the text. Now, when we talk about trigonometric integrals, there are essentially three varieties. There are products of powers of sines and cosines. Products of powers of sines and cosines. The second variety is products of powers of secants and tangents. And we'll see what these mean here in just a bit. And then the third possibility is a mix of these two. All right? So, I'm going to start with something that I think you know about. You should be able to do this. Suppose we have sine to the third of x times cosine of x dx. This is a Calc 1 problem. This is an ordinary garden variety Calculus 1 U substitution. It's not a basic form, and so if someone says it's a Calc 1 problem and it's not a basic form, then the only other tool in your Calculus 1 toolkit is U substitution. And so the question is, what are we going to choose U to equal? Well, we have a function being raised to a power. Remember that sine to the third of x means sine of x to the third power. That's what that really means. This is just shorthand notation. So back in trigonometry, we learned that. If I have sine to the third or sine to the fourth of x, this actually means sine of x to the third or the fourth or whatever. And so we have sine to the third cosine x. Well, we can let u equal sine of x, the inside function, just like we always do. And now we have to account for everything else. Notice, and this is the key to this first procedure, if you let u equal sine, then du, in the differential, you're going to you're going to require that there is a factor of cosine. Well, in this particular case, because this is a Calc 1 problem, that's exactly what happens. But what we're going to do is we're going to ensure that this happens and then account for everything else that's in the problem. Now, the rest of this goes through straightforwardly. The substitution is now exact. This is sine cubed means sine, which is the u expression, to the third power. So this is actually u to the third. This piece that you have reserved off for the differential, right? This is the differential. That part is simply du. When you do this procedure accurately, what you inherit from this is not particularly challenging. In fact, it's a basic form. This is the most basic of the basic forms. This is the power rule. U to the fourth over 4. And then we go back to the original expression, u was sine of x. So you can write this either using this sort of notation, or it's simpler to use this notation, sine to the fourth over 4, and you're out. And so that's the Calculus 1 problem. What we're going to do is leverage our knowledge of how this works, and then it's going to be more complicated, so we have to figure out how to take the more complicated stuff into account. So, our next little example, and this is the newer version. Suppose we want the integral of, let's go sine squared of x times cosine to the third of x dx. So this is the product. Things are being multiplied, not added or subtracted. This is the product of powers. See what it says? Products of powers of sines and cosines. Products of powers of sines and cosines. Now, here's the piece. The derivative of sine is cosine. The derivative of cosine is sine. That's why sine and cosine play well together in this procedure. The derivative of sine is expressed in terms of cosine, and the derivative of cosine is expressed in terms of sine. It's not exactly that. The derivative of cosine isn't sine. It's expressed in terms of sine. Well, similarly, the derivative of secant, it can be expressed in terms of secants and tangents. And the derivative of tangent can be expressed in terms of secants and tangents. In fact, can be expressed in terms of secants alone. That's why these play well together. When you let u equal sine, if we were to let u equal sine in this problem, du is cosine, and we have some cosine there to account for it. If we were to let u equal cosine here, du is expressible in terms of sine, and so we have sines here to account for that. Similarly, if we had a problem involving secants and tangents, if you let u equal tangent, du, the differential, is secant squared. We can leverage the secants in the problem to make that happen. So that's what's going to go through this process here. Similarly, if we let u equal secant, then we have a way to express that differential. So here, case number one, the simplest version is, so case number one, if either, it could be both, if either of these exponents is odd. If either of these exponents is odd, this is easy money. If you have a choice, remember, if it's cosine to the first, this is cosine to the first, 1 is an odd number. All right. So if you have the choice of two, if they're both odd, then typically you choose the smaller of the two. It just makes the algebra less gnarly. If they're both the same size, pick one and go with it. If either exponent is odd, then here's what we're going to do. Peel off one, in this case, cosine of x. So in our case, cosine of x is the odd exponent. Peel off one factor of, in this case, cosine. If sine had been the odd one, peel off one factor of sine. And here's what I mean by that. I'm going to rewrite this. I want one factor of cosine because I know pretty soon I'm going to do a u substitution, which means I'm going to create du, which means du needs to have that factor of cosine in the expression. I'm going to peel off one factor of cosine, and this is reserved. Nobody gets to use it. That's reserved for the differential. So see what I did? I peel off one of these factors of cosine. All the others, in this case, there's 2 left, go here in the original expression. So this cosine is reserved. Nobody gets to sit at this table. Cosine is reserved. If you peel off one factor of cosine, now you convert all factors to the other function. By that I mean, if you reserve off cosine, everything else gets changed to sine. If we had reserved off sine, then everything else gets converted to cosine. Whatever you peel off for the differential, you cause these other functions to be the u expression that's going to create that differential. Let me say that again. Once you reserve this function, you cause these to become, or express these in terms of, the function that's going to produce this differential. What function produces cosine as its derivative? Sine. Everything here needs to get converted to sine. If they already are, so much the better. But if they're not, we know how to change cosine squared into sine, because now this is sine squared. Cosine, I know what that is. That's 1 minus sine squared of x. And now cosine of x is still here. Dx is still, this is still reserved. I always box this off. This is reserved. Nobody gets to play with it. Distribute. I'm going to run out of space, so I'm going to steal my spot here. So if we distribute sine squared, we get sine squared of x minus, we see, sine to the 4th. But I still have cosine of x and dx as the differential. Once you express everything in terms of the other function, and simplify that expression, now this is an ordinary Calc 1 u substitution. Let u equal the other function. Not to the second power, not to the fourth power, just the other function. If you reserve cosine, let this be the other function. Let this be the function that creates the differential. If this is cosine, sine creates a differential. If this is sine, cosine creates the differential. If this is secant squared, tangent produces that differential. We'll talk about that next up. So we have chosen u to be the function that creates this differential. Well, let's go ahead and create it. The derivative with respect to u, the derivative of sine is cosine, and the substitution is exact because we forced it to be exact. You're forcing the behavior of this u substitution way back here at the very beginning of the problem. By reserving this off, everything else is straightforward. This is now, the substitution is exact. This is sine squared, so this is now u squared minus u to the fourth. Cosine x du x is just du. And power rule. Everything, there's not a lick of calculus up here anywhere. Look, there's no calculus anywhere. The calculus is driving it. Everything here is trigonometry. But you're getting your ducks in a row so that the antiderivative works out to be very easy. This is like a whole lot of trigonometry, little bitty calculus. So the antiderivative, this is u to the third over 3 minus u to the fifth over 5, and the constant. Go back to the original variable from the let statement and you're out. This, right here, in that box, that's the only calculus in the entire problem. Look at it. Now, the reason you're doing this is because of the calculus. But this is the only real calculus computation. There's a few other little details. But this is the only real calculus computation you're working. What was u? U was sine of x, so I have sine to the third over 3 minus sine to the fifth over 5 plus the constant, and we're out. So we'll practice several examples of this, and this should become just bread and butter for your work in trigonometric integrals.